Alright, here we go again. So the other day I asked you to do some problems where we were rotating the curve around the y-axis instead of the x-axis, and then things got away from us in a hurry because they decided to have us do two curves instead of just one. So let's tackle that today. So this says find the area of the region enclosed by the curves y equals x and y equals x squared as it's rotated around the x-axis. So here's our setup. So we're taking this little tiny in-between piece right here, and we are going to spin that around the x-axis. And so I don't know what kind of visual you get from that. Sort of a funky bowl, I guess, with the middle, the outside's like flat, and then the inside is sort of curved somehow anyway. So this is basically the same thing as we were doing when we extended our use of integrals from finding the area underneath a curve to find the area in between two curves. I'm basically going to find the area or the volume that I would get from a solid if I took this and rotated it around the x-axis, and then I'm going to subtract from that the volume of the solid that I would get if I took this curve and revolved it around the x-axis, and then hopefully you can kind of visualize that what would be left would be the spaces in between. Okay, so the way this changes our setup is that now we have two radii that we're interested in. I use the little subscript O here to represent the outer radius, so that is the radius that is the farthest away from the axis of rotation. And then we're going to subtract from that pi times the inner radius squared, and so that's the radius that is closest to the axis of rotation. And then of course it's easier if you factor the pi out and just do it like that. Okay, so in this case our outer radius is y equals x, and our inner radius is y equals x squared. And so that would look something like this. I would have pi times the outer radius squared, so pi times x squared, minus the inner radius squared, and the inner radius is defined by the curve y equals x squared, so that would be minus x squared squared. So if I simplify that a little bit, the area of my cross sections that I'm going to integrate, that I'm going to add up an infinite number of these tiny little guys, is pi times x squared minus x to the fourth. All right. So to turn that into an integral, look at how techie I'm getting. Figured out how to do an integral symbol on this little flip chart thingy. Again, I'm going to factor the pi out because that's a constant. My limits of integration are 0 to 1 because these two curves cross at 0, 0, and they also intersect at 1, 1. So I'm doing pi times the integral from 0 to 1 of x squared minus x to the fourth dx. Alright, so that is a very easy antiderivative to do once we have it all set up. The antiderivative of x squared is, of course, 1/3 x cubed. The antiderivative of x to the fourth is negative 1/5 x to the fifth. And then I would plug in 0, which would give me 0, and then I would plug in 1, which would give me 2/15. So my final answer for this is 2 pi over 15. All right, well, now that we've introduced the idea of revolving something or more than one curve around something, we can also change the axis of revolution. So I'm going to take the same situation as we had in the last example, where I'm taking this little tiny piece in between these two curves, but instead of revolving it around the x-axis, I'm going to revolve it around the line y equals 2. So I have to do the same thing with this as I was doing with the other one. I'm going to take the outer curve, which in this case now is y equals x squared, because we're looking for, when I say outer curve, we're looking for the curve that is the farthest away from our axis of revolution. So that's y equals x squared. So I'm going to go this curve minus the axis of revolution, minus this curve minus the axis of revolution. And so that looks something like this. So the area of my cross sections in this case, since they're still circles, they're still cylinders, is pi times, oh, I went the other way around because this one is actually above this one, so I have to go top to bottom. If I went bottom to top, it wouldn't actually matter because we're squaring it and everything would switch around to be positive. But just to stay conceptually accurate, we're going the top curve minus the bottom curve, so 2 minus x squared, this minus this, and then we're revolving that around here, so that makes it a circle. That's why it's pi times this squared, minus pi times, again, the top curve minus the closer curve, x squared. So this is what the cross sections of this would look like, okay? Okay, so we can simplify that considerably. If I FOIL this out, that's 4 minus 4x squared plus x to the fourth. If I FOIL this out, I get 4 minus 4x plus x squared. And then I have some like terms that I can combine. I'm subtracting here, so I'm going to take the pi and put it out in front, and then I'll write this in kind of better order. So I've got x to the fourth, and then minus 4x squared minus x squared is minus 5x squared. Then where's my 4x? Okay, minus 4x gives me this 4x, and then this 4 minus this 4 cancel each other out. So it turns out this is the integral that I'm going to do, which again is not very difficult. I'm going from 0 to 1 because those are the intersection points in between these curves. So I have to take the antiderivative of this. Ooh, that looks like fun. So the antiderivative of this is 1/5 x to the fifth. The antiderivative of this, since I'm adding 1 to the exponent, is negative 5/3 x to the third. And then the antiderivative of 4x is 2x squared. So I haven't figured out how to make a little bracket here yet to show that then I'm plugging in 0 and 1, but that's what I'm doing. If I plug in 0, I get nothing, so I don't have to worry about that. But if I plug in 1, then I would get 1/5 minus 5/3 plus 2, which if I write using the common denominator 15, 1/5 is 3/15, 5/3 is 25/15, and 2 is 30/15. So altogether, that simplifies down to 8 pi over 15 as our final answer. All right, so what we're doing here is solids of revolution. If it's a solid disk, then all we have to do to find the cross-sectional area is go pi times the radius squared. If it's what's called a washer, so there's a hole in the middle because we have two curves, then the cross-sectional area is pi times the outer radius squared minus pi times the inner radius squared. And once we understand that, then the sky is the limit. I could take the same setup here, and instead of rotating this little area around the x-axis, instead of rotating it around the line y equals 2, I could revolve around the axis x equals -1 and go this way. Okay, so I'm going to take this now and rotate it sideways around the line x equals -1. So now since we're going sideways, things change a little bit. So my my cross sections are going to be in terms of y, not in terms of x. So, but again, I'm going to take the outer curve, which is the farthest one away from the axis of revolution. So in this case, that's y equals x squared, minus the axis of revolution, which is -1. And then for my inside one, I'm going to go pi times the inner curve, which is this guy right here, again, minus the axis of revolution. But notice that our axis is x equals -1, so to be consistent, we have to change these to x equals also. Y equals x is already set up for that. That just means x equals y. But this one we're going to rewrite as x equals the square root of y. I'm sure this is not the easiest thing to learn without the ability to ask your teacher questions, but I just went and switched all the y's to x's just because we're more used to that. Okay, so this is pi times the farthest away curve, which I again solved for x, or and made it square root of y. Minus -1 is really +1, and then this one is minus pi times x plus 1 squared. Okay, so a little bit of algebra with this. FOIL this out, you get x plus 2 root x plus 1. FOIL this out, you get x squared plus 2x plus 1. Then we can go through and combine some like terms and end up with this as the area of our cross section that we're looking to integrate. Okay, so the integral sets up like this. I changed the square root of x to an x to the 1/2. We're still going from 0 to 1 because that's where these things cross. So I can go through and do those antiderivatives. -1/3 x cubed for this, -1/2 x squared there, and 4/3 x to the 3/2. Conveniently, we only have to plug in 1 again because when you plug in 0, everything cancels out. So when I do that, I end up with -1/3 minus 1/2 plus 4/3, which turns out to be a fairly clean pi over 2. All right, so that's fun and games with solids of revolution. There's a lot more that you can do with this. So here's a problem where what you're doing is you're taking a circle and then you are stacking equilateral triangles on top of the circle. So the height of the equilateral triangle depends on the width of the circle at that point. And you get this funky looking shape like that. So in this case, your cross sections would be equilateral triangles. You can also take this one right here. Oh, this is, showing the math, how they get the answer for that. We could do another one. We could prove the formula for the volume of a pyramid by taking a thing with cross-sectional areas as squares. And then we could also do this totally wacky one with a wedge cut out of the cylinder. And hopefully you can see that this, has some useful applications when you get into some upper level engineering. But we're not going to go through these problems. These are hard enough to do when we have the opportunity to chat in person and ask questions. I'm not going to try and do that remotely. Plus, none of you guys are actually watching these videos anyway, so not really sure why I'm bothering. Anyway, if you want, you could now go back and do the assignment that I gave you the other day, because you know how to do all of this. I'm not going to go through and make a video of me doing these problems unless somebody requests that I do that. So I'm going to continue to just put content out there, but I think I'm only going to respond to specific questions that we all have. So that means that tomorrow, we will jump ahead. I think we're at the point in the course where we start picking and choosing a little bit to 6.5. Yeah, so average value of function, way easier than what we've just been doing. Pretty simple formula for that. So don't forget to tune in tomorrow to see what that's like. Okay, hope you all are doing well and taking care of yourselves and each other. Bye.